So here now we will talk about the introduction to dynamic analysis. Um, Here the discussion between the professor and students. So introduction to dynamics. Let's start with the dynamic loads. What are they? Basically, what are the dynamic loads? Dynamic loads means that changes with the time. Dynamic loads change with the time, like waves pushing the structure and pulling the platform constantly. That kind of some changes keeps happening. The loads keep changing with respect to time. Those loads are called dynamic loads. Exactly, like unlike static loads, these are not constant. So unlike static loads, dynamic loads are not constant. So dynamic loads are varying with respect to time. Static loads should be constant. So the structure does not just sit still. Yes, in dynamic analysis, when we are doing it, the structure, if the load apply load is keeps varying, the structure also does not just sit still. It moves or vibrates. So why does this matter? The dynamic analysis, why does this matter? Because these vibrations can cause extra stresses. Why does this matter? Because these vibrations can cause extra stresses. We must design for that. So these extra stresses, whatever is coming, that should be designed also. Our structure should be safe to handle all these loads, right? Okay, so next we will discuss about the natural frequency and modes. The beam vibrates in different ways. You see the second student 2 draws a vibrating beam on the board. If you see, the beam vibrates in many different ways. That means different way it is going to vibrate. So each way is called one mode shape. So each way is a mode shape. So and each mode has natural frequency. Frequency means how fast it vibrates. If for example, if you are going to some place very frequently, that means what? You are coming, your speed is very fast, right? If the frequency is more very highly frequently you're coming, means it completes the cycle very fast. And very low frequency means you are coming, the time it takes for you to come back to some place, it takes a lot of time. That means low frequency. And for example, if you are going someplace every week, that means your frequency, you can say more. But if you are going to some place like after 1 year or every year, that means your period, the coming back period is less. So natural frequency and period, these two are inversely proportional. So for each frequency, means if you say some frequency, it means like how fast it vibrates, how fast it's very fastly vibrating or very slowly vibrating. That kind of details we can come to know from a natural frequency. For example, if we say natural frequency as 0.1 hertz, that means like 1 by 0.1 is 10 seconds. 10 seconds means it takes 10 seconds to complete one cycle. Suppose if I say the frequency is 1, that means my period is also 1 second. That means within a second it's completes the cycle. That means it's very fastly vibrating it, right? So frequency is high means very quickly it vibrates because period is less. Quick means period is less. Slow means period is more. So that's why each frequency has its own vibration speed. Each mode shape has one frequency. That frequency means how fast it vibrates. For example, if you have a simply supported beam or cantilever beam, for example, you take a cantilever beam, the first mode will be like this. So this mode means the period will be more. This is the first mode. For this mode, we will be having a period. That means frequency. It will be the lowest frequency. Always the lowest frequency is the natural frequency we used to call. Okay, that means it takes more time. This is 3 seconds, for example. If it takes that's the frequency slow. If it takes like 10 seconds, that means the frequency is high. Okay, so what controls this frequency? It depends on the structure stiffness and modes. We have to ask like, okay, the structure vibrates fast or slow, that means it has its some frequency. What controls this frequency? Why some structures more frequently vibrating? Some structures are taking a lot of time to vibrate to complete one cycle. It all depends on its mass and stiffness. If more stiffness means high frequency. If stiffness is more, high frequency means it takes less period. And if mass is more, means it lower frequency. That means it takes more time period. Okay. We find these frequencies using eigenvalue analysis in TimePack. We have some software called SAX. We use that module TimePack that helps us to do the eigenvalue analysis that give us the frequencies. Okay, importance of mass participation. Mass participation shows how much of the structure's mass. For example, if I have a 1,000 ton deck, in the 1,000 ton deck, now from first mode, for example, I am taking the first fundamental mode. In that mode, how much of the mass it moves along with that during that mode, how much mode participates in that movement, how much mass participates in that movement for that particular mode. That will be shown by this mass participation factor. Why do we care about that? Because modes with the low mass participation don't affect the structure much. Modes with the low mass participation factor don't affect the structure much. We want to include the modes that cover almost 100% of the mass to get the full picture. I just want to get the full picture how it's going to behave. So that means like I want to get almost 100% of the mass, but that's not practically possible. So at least if it more than 95%, 90%, that should give some reasonable and reliable picture. Resonance and safety, you will see. What happens if the natural frequency is close to the wave frequency? We know wave frequency, for example, most of the waves it will be more than 6 seconds and even 10 seconds, 12 seconds, like that. Wave periods are there, and structural period may be around some less than 3 seconds. So these two are far away. It's not close to the wave frequency. Natural frequency is not close to the wave frequency. Suppose if it happens, what happens if the natural frequency is close to the wave frequency? That means that's resonance. During resonance, the structure can vibrate more. If vibrates more, and it get damaged also. If it vibrates more, means what? Like it's moving left and right. When something is moving, it will create some inertia force, right? Those additional forces. So additional force means it's going to cause additional stresses. Then structure may get damaged, right? So we should avoid the resonance. How? By design or by using damping, or we make the structure stiffer or heavier to change its frequency. If we change the frequency, if we keep the frequency away from the wave frequency, then we are avoiding the resonance. Okay, that's the by design. Dynamic amplification factor. DIF tells us how much bigger forces get because of vibration. Due to this vibration, how much bigger the forces get amplified. That's why I use this DIF factor. We multiply the static forces by DIF to get the design force. Yes, that's correct. It makes sure. Why do we do that? It makes sure we don't underestimate the loads, design loads. Dynapack and sags. Dynapack calculates what are the things we get from the Dynapack. What are the important things like mode shape and frequencies. Frequency means like how fast each mode is vibrating, or how slow each mode is vibrating. And mass participation. Mass participation shows like for each mode how much of the mass it's participating. Suppose some particular mode the mass participation factor is low, means that's not going to affect the structure much. SACS uses this data to check stresses and code compliance. This combined approach ensures the safe design under dynamic loads. And also final design checks what we are doing. And also we check piles for axial capacity under amplified forces. We check jacket members and stresses for buckling. And if anything fails, we update the design and rerun the analysis again. This process keeps the platform safe in storms and waves.